Okay. Good afternoon, lads and ladies. Today we are going to continue our foray into calculus by taking a big step. Big step being, you are now done with differential calculus. All right, half of it, half of the whole thing, you're done with it. The other half of the whole thing is what we spend the first third of Calc 2 really refining. And we spend the last kind of quarter of Calc 1 introducing and getting you used to. There's really two different branches of calculus. The first being the stuff that we've been doing, differential calculus, where you differentiate to find a derivative. And that has to do with like rates of change, approximation, bilinear functions, all of the things that you've seen us doing. The other side of that coin is integral calculus. And integral calculus aims to solve entirely different questions at the start. But then we'll discover that they're actually linked to each other in a really interesting way. And I'm going to approach the subject by first sort of showing you something called an antiderivative, and then showing you a completely different problem than any of the stuff we've seen, and then tying those two things together. So it's going to require a little bit of patience on your end, and it's going to require kind of a willingness to remember this week's lesson next week. So without further ado, let's get rolling. That's right, this pen has been misbehaving, so we're going to use this one. Today is the 6th. I know you all took your exams. If you haven't taken exam 2 yet, if you did not take the exam on Wednesday for whatever reason, sick or we had some other arrangement set up, anything like that, please contact me to verify that we have arrangements. Or if you haven't contacted me yet and you didn't take the test for whatever reason, I don't care, right? Flat tire, grandma was sick, you were sick, overwhelmed by election stress, whatever. Reach out to me and let's have a conversation so this can go as well as possible. That is, of course, critical because nobody wants a 0 on a test. At the similar kind of token there, make sure you hand in the study guide. Not everybody has handed in the study guide yet. Remember, it is not sufficient to just solve the problems in WebAssign. To get the grade for the study guide, you must submit the written work for the study guide problems in Canvas. Today, we are going to talk about antiderivatives. And they are what they sound like. If a derivative is a thing, we know what a derivative is. An antiderivative is the undoing of that thing. No, I have not marked all the study guides yet. No, there are actually many study guides that I have not marked yet. So the section numbers here are going to jump around just a little bit. We are going to, I think antiderivatives are section 4.9, and then we're going to move into 5.1 and 5.2. But today, is section 4.9. And if there's time, I'll introduce 5.1, 5.2, but probably not. Probably today, just this. Your homework, you may have noticed, has some problems relating to area, finding areas under curves. Because I don't expect to get to that material today, I have extended that homework. That homework is not going to be due on Monday of next week. It's going to be due on Wednesday of next week, which will give us some time on Monday of next week to fill in the bits that we're not going to get to today. All right, so definition. Given a function little f of x, an antiderivative for f of x is a new function capital F of x satisfying capital F primed is little f. Right, so an antiderivative is a function whose derivative is the function you were given. Right? You want to find somebody who differentiates to your function. So let's look at some examples. Maybe also I'd like to make a note here. I'm using the word "an" rather than the definite article "the." We use the indefinite article "an" because given a particular function f of x, there is more than one antiderivative. So you'll hear me saying an antiderivative rather than the antiderivative. And I'll talk about the details in just a second. So, example. If little f of x is 2x, then an antiderivative is capital F of x equals, well, who differentiates to 2x? What function can you take the
X
derivative
squared.
and get 2x? Yeah, x squared. Why? Because capital F primed of x is x squared primed, which is 2x, which is little f of x. So capital F primed is little f. That's it. In fact, you can think of derivatives as like a ladder, right? You can go up the ladder and down the ladder. You can take derivatives and you can take antiderivatives, right? You can find the derivative of the derivative of the derivative of the derivative, or you could go back the other way and find the antiderivative of the antiderivative of the antiderivative of the antiderivative. You can think of it as a chain or a ladder on which you can walk both directions. That's usually the language. Okay, bonus round. Little f has x squared here as an antiderivative. Can anybody think of another antiderivative? Another antiderivative for this same function, f of x equals 2x. Are there any other functions that have this guy as their derivative? Yeah. Good. Yeah. Another example here that would work is, like Sophia said, x squared plus 2. Because then capital F primed is x squared plus 2 all primed. And the 2 differentiates to 0. Any others? Somebody else give me another antiderivative for this function? Right, so x squared plus 2 also has derivative 2x. So x squared plus 2 is also an antiderivative for 2x, not just x squared. Another example, how about x squared minus 4? Yeah, well, yeah, this works also because, again, the derivative of this function is 2x minus 0, which is still 2x, so that is little f. What about x squared plus pi? Is that an antiderivative for 2x? Well, sure it is, because if I differentiate the function x squared plus pi, just like the 2 and the 4 differentiate to 0, the pi differentiates to 0. So we get 2x plus 0, which is again little f. You can kind of feel where this is going, right? There's not just one antiderivative for this function. There's not just x squared, but also x squared plus 2, or x squared minus 4, or x squared plus pi. The most general form antiderivative for f of x equals 2x is x squared plus any constant. And when we talk about these, we like to use the symbol capital C for that arbitrary constant, meaning if you differentiate x squared, you'll get 2x. That's great. If you differentiate x squared plus or minus any other number, like x squared plus 5 or x squared minus 7 or x squared plus pi, you'll also get 2x. So here the number c, it's called an arbitrary, meaning I don't care what it is, constant. And when you calculate the most general antiderivative for any given function, it's going to go this same sort of way. You're going to find like the core antiderivative, the thing that when you differentiate it becomes your function. But then you realize, oh, well, I could also have slapped on any constant I wanted, and that would still have the same derivative because the constant piece always differentiates to 0. Making sense? Geometrically, there is an interpretation here. There's a way to think about this in terms of graphs. Oh, real quick, if you're interested in divergence, curl, Maxwell's equations, the speed of light, the way electricity and magnetism behave, this video from 3 Blue 1 Brown is the best thing I've seen in a long time. There's lots of videos out there. MIT has some really good ones, but this video, divergence and curl, the language of Maxwell's equations, fluid flow and more, really good stuff. Okay, here's decimals. So this was some other stuff I was doing for Calc 2. This is pretty cool, right? But let's focus on our thing. So my original function is 2x. I claim that an antiderivative for this function is x squared, but also x squared plus 1. I'll have to zoom out here. X squared plus 2, x squared plus 3, x squared plus 4. And we could go the other way. We could do x squared minus 1, x squared minus 2, x squared minus 3, x squared minus 4. So forget about the connection between little f and big F for just a moment. If you look at all the antiderivatives in general, x squared plus c, what you're really looking at is all the vertical translates of that core antiderivative. So all of these functions have derivative 2x. And the geometric way to think about these is that when you're asking the question, what is the most general antiderivative? The answer isn't a single function. The answer is an infinite family of functions, which are all vertical translates of each other. Think about it, if you shift the whole graph up or down, that doesn't change the slope of the tangent line at any given point. So if I look at x equals -2 on the black graph, the slope here is the same as it is on the purple graph, is the same as it is on the green graph, is the same as it is on the blue graph, right? These all have the same slope at x equals -2. And the same is true everywhere. They all have the same slope at 0. They all have the same slope at 1. You get the idea. So when you're computing the most general antiderivative for a function, first you find your core or basic antiderivative, and then you slap on a plus c. That's it. Because any function of this form will have this as its derivative. All right, let's ask the question in a bit more generality, maybe through a few more examples. So let's find the most general antiderivative of the function f of x equals, how about 3x squared minus x plus 7. So I'm trying to think of a function that differentiates to this. Well, what function has derivative 3x squared? Who, when you take his derivative, gives you 3x squared? Yeah, so if he's got it in chat, x cubed, right? The derivative of x cubed is 3x squared. So the antiderivative for 3x squared, or the core antiderivative for 3x squared, is x cubed. Who has derivative negative x? Or you can think of the minus as just coming along for the ride and asking who has derivative x. This is not quite as obvious. Well, if it's going to differentiate to x to the 1, you know it's got to be an x to the 2, right? X to the 2, though, differentiates to 2x to the 1. So in order to get rid of the 2 that comes down when you take the derivative, you need to divide by 2. So this piece has this antiderivative. You can check. If you take the derivative of x squared over 2, you don't need a quotient rule. The 2 downstairs is constant. It's just 2x to the 1 over 2, and the 2's would cancel. And then who has derivative 7? What function can you think of when you take its derivative, you get 7? Well, that's just 7x. So the most general antiderivative is this plus c. And we can check. If I differentiate capital F, the derivative of x cubed is 3x squared minus the derivative of x squared is 2x, so this is 2x over 2, plus the derivative of 7x is 7, plus the derivative of any constant is 0. The 2's cancel, and you do get 3x squared minus x plus 7, which is little f. So this is your most general antiderivative. This is your answer right here. Oops, shit, the 2 should be included, sorry. This is hinting at a more wide-ranging rule that I will show you now. First, there's a backwards power rule, or a reverse power rule. It says if little f of x is x to the n, then an antiderivative, big F, is x to the n plus 1 over n plus 1. So if you want to find an antiderivative for a power function, you add 1 to the power and then divide by that new power. The proof is very simple. The derivative of x to the n plus 1 over n plus 1, we bring the power down, so that would be n plus 1 times x, and then we subtract the 1 from the power, n plus 1 minus 1. And then the over n plus 1, that's just a constant, that just comes along for the ride. But of course that denominator, that's n plus 1 times 1, so I can cancel. And n plus 1 minus 1 is just x to the n. That's it, that's the proof. The catch is that this works great for all x's except, or for all n's except one of them, namely -1. 1 over x is special. X to the negative first power is special because he is not the derivative of any power function. I'll address that separately in a second. But again, here are the things you need to remember. Well, we should include this, sorry.
Quick question, how would a limit work out when, could you do a limit as n approaches -1?
N, you take a limit as n approaches -1. Interesting.
Or like the,
well,
yeah.
so the thing is, we don't really have an operator for the antiderivative yet. We'll learn that, of course, that's called an integral, if you're familiar with it, as I suspect Alex may be. But we don't know how the integral operator or the antiderivative operator, whatever that thing is, would interact with a limit. So we don't know if limits and take the antiderivative can be done in whatever order we want. It turns out that question is actually pretty subtle. You will not get the antiderivative for 1 over x as a limit of derivatives of powers of x. So it turns out in this case that those operations don't commute nicely. But for now, this is what I'm asking you guys to remember. Is that if you want to take an antiderivative of a power function, as long as the power isn't -1, then you add 1 to that power and divide by the new power. The other kind of basic thing we need to introduce here is that antiderivatives play nice with addition, subtraction, and multiplication by constants. So if capital F and capital G are antiderivatives for little f and little g, then call it capital H as a constant a times capital F of x plus little b times capital G of x is an antiderivative for little h, which I'll call is the name I would give to a times little f plus b times little g. In other words, antiderivatives, you can do them one piece at a time. right? If you can split something up into a sum or linear combination of different functions, you can anti-differentiate each piece on its own. That's what we did here, right? I took the antiderivative of this, then I took the antiderivative of this, then I took the antiderivative of this, and just put them all together. This theorem says that's legal. We can do that. Again, the proof is easy. So let's differentiate capital H. That's the derivative of a times capital F of x plus b times capital G of x. And then because of the way the derivative works, this is a times f primed of x plus b times g primed of x, right? You know, you can differentiate each piece on its own and that constant multiples come along for the ride. But then a times capital F primed is a times little f, because capital F is an antiderivative for little f. And b times capital G primed is b times little g. And what is this? A times little f plus b times little g, that's little h. So again, the proof is very simple here. And the basic idea is one that I think everybody would have guessed or even assumed they could use without me telling you. And that's that, yeah, you can add and subtract and multiply by constants and everything works out great. All right. So these two rules together are enough to allow us to find antiderivatives for any polynomial. The theorem at the bottom says you can find an antiderivative just by taking antiderivatives of each piece. And the blue box statement above says how to take the antiderivative of any piece of a polynomial. So let's try one more example with a polynomial, and then we'll go a little deeper. First, any questions on these two statements here? All right. Let's find the most general antiderivative. I said this would be a polynomial, but I'm changing my mind a little bit. It'll still look a lot like a polynomial. Let's do f of x equals x to the 4 minus 2x cubed plus 3x squared minus 2 square roots of x. So I want to find a function who has this thing as its derivative. And the point of the theorem on the previous page is that you can find this piece is antiderivative, this piece is antiderivative, this piece is antiderivative, and this piece is antiderivative all separately, and then just put them together. So what is an antiderivative for x to the 4? What did that power rule say? I'm gonna hold on this till I get an answer. Yeah, good, perfect, Harris. X to the 5 over 5. We need to add 1 to the power. Who's going to differentiate to x to the 4? That's got to be something like x to the 5. right? Because the derivative of a 5th degree polynomial is a 4th degree polynomial. So this has to be x to the 5. Oh, but then when you differentiate x to the 5, you get 5x to the 4. I need to get rid of the 5, so we'll divide by 5. X to the n plus 1 divided by n plus 1 is the antiderivative for x to the n. It's the core antiderivative for x to the n. All right, moving along. Minus 2 is going to come along for the ride. And then an antiderivative for x cubed, same pattern, is x to the 4 over 4. And these two will be able to play together. Plus the 3 comes along for the ride. An antiderivative for x squared is x cubed over 3. And you can see how well that rule works. Even in a setting where you already knew, oh, this is the antiderivative, this is x cubed. Well, the 3's will cancel and you'll get x cubed. The rule works. Okay, here's the catch. What the hell do I do with root x? Let's come off to the side for a minute. Root x is x to the 1/2. No antiderivative or anything, that's just what root x is. So if I apply the power rule to that, I will get, I'm just going to use a squiggly arrow here for I will get, x to the 1/2 plus 1 divided by 1/2 plus 1. Well, what is 1/2 plus 1? It's 1/2 plus 2 over 2. It's 3 over 2. So this is x to the 3/2 divided by 3/2. That is your antiderivative for x to the 1/2. So this last piece will be minus 2 times x to the 3/2 divided by 3/2. And then, of course, we need to tack on a plus c because we want the most general antiderivative. You can and should simplify this. So my most general antiderivative written nicely, I would write it as 1/5 x to the 5 minus 2 over 4 is 1/2 x to the 4 plus 3 over 3 is 1 x cubed. And then here you have to do your flip and multiply business. So this will be minus 2 times 2 over 3 is 4/3 x to the 3/2 plus c. So this would be your final answer written nicely. So the power rule works great. This rule that says just add 1 to the power, then divide by that new power, it's dope. Does the job for a lot of functions. There's one function, one power function, for which it doesn't work. This works great for all n except -1. So I want to pay special attention to that guy now, and then look at a couple more examples. First, any questions on this example?
Wouldn't -1 just be natural log?
Ah, yeah, you beat me to it. Exactly. That's exactly correct. So what about the n equals -1 case? Well, if f of x, little f, is x to the -1, that's the same as 1 over x. Who has this as a derivative? ln x is a good answer. Because we know that the derivative of ln x is 1 over x. Right? Because the derivative of ln x is 1 over x. But there's a small catch here. This function, little f, what's his domain?
All real numbers?
Not quite all real numbers. Look at the far right version
Oh,
here.
all but
over-
0.
Yeah, everybody except 0. What's the domain of the natural log?
All above 0.
Yeah, just the positive numbers. So if x is greater than 0 and little f is 1 over x, then capital F is ln x. But what if x is less than 0? Or what if you have a combination of the things? What if I want to do something with this antiderivative that involves values of x that are suitable to plug in here, but aren't suitable to plug in here? Turns out the most general antiderivative for 1 over x of course, there's going to be a plus c involved, but there's something else a little bit more subtle here. It's the natural log of the absolute value of x plus c. Reasons here will take a second for me to explain, but at the very core of it, at least you can understand that the problem is the domains don't match. The domain here is just positive numbers. The domain here is positive or negative, as long as you're not 0. So I'd like an antiderivative that works for this function everywhere it's defined. And it turns out, I claim that this is the one which works. Of course, the plus c will differentiate to 0, so I'm going to ignore that and just think about this. Switching to Desmos in 10 seconds. Okay, switching to Desmos now. The vertical translate stuff is nice. That's the best way to understand the question, what is the most general antiderivative? It's just all the vertical translates of the core antiderivative. But let's look at, all right, and here. So if I focus just on the positives, here is your original function, and here is, oh, sorry. Here is an antiderivative. So you can see that the green is the derivative of the derivative of the green is the red, right? If I look at this guy, for example, here at the point 1, or where x is equal to 1, the slope of the graph here is the y value of the graph here. And as we get closer to 0 here, these slopes, they're large and positive, so the derivative is large and positive. And as we run off to the right, the slopes here are getting shallower and shallower, still positive, but getting shallower and shallower, meaning that the tangent line slopes are getting closer and closer to 0, which is what the red function does. But if I don't restrict the domain of the red function, and I ask, well, what about these guys? Are these guys describing the slope of any function? Look at the symmetry here. The red function has this origin symmetry. So I would expect its antiderivative to have some sort of symmetry as well. And if I swap ln x for ln absolute value x, oh, it doesn't like that, does it? There we go. you'll find that the symmetries make sense. Let me look over here, for example. When x is -1, the absolute value of -1 is 1, so the natural log of the absolute value of -1 is 0, so the point -1, 0 is on the green graph. What's the slope of the tangent line here? Well, it should be the same as the slope of the tangent line over here, just negative, right? Because this guy is symmetric to this guy. Same steepness, just pointing down here instead of pointing up here. So the slope of the tangent line here should be -1, should be the point symmetric, and it is. Sorry, my mouse clicking is not going so great here, but son of a bitch, there it is. So the most general antiderivative, and all the same stuff I said before carries over here. As you go off to the left, the slopes are getting more shallow, but they're all negative slopes. So this should be getting closer and closer to 0, but still negative. As you go down towards this vertical asymptote, these slopes are getting negative and enormous. So the derivative should be getting negative and enormous. The upshot is this. Most general antiderivative for 1 over x is natural log of the absolute value of x plus a constant. If x is positive, then you can forget about the absolute values. But if you're not told that x is positive, you need the absolute values. In your homework problems, some of them will say, do this with the assumption that x is greater than 0. And in that case, you can just say ln x. But if they don't tell you to assume that x is greater than 0, this is your antiderivative. Let's make use of this now and also kind of practice a little bit more standard antiderivative problem where you've got more to do than just apply the power rule. The bottom of this page has some other stuff, so I'm going to try to keep it out of camera, but if you see some other junk floating around like down here, don't panic. All right, let's try to find the most general antiderivative for x cubed minus 2x squared plus 3x minus 5 all over x squared. Derivatives play nice with addition and subtraction. So antiderivatives play nice with addition and subtraction. Derivatives play nice with multiplication by constants. So antiderivatives play nice with multiplication by constants. However, derivatives do not play nice with division, right? If I wanted to find the derivative of this instead of an antiderivative, I would need the quotient rule. There's no nice backwards quotient rule. So what we need to do before I can even begin looking for an antiderivative is write this in a form that my antiderivative rules apply to. So far, the only things I know how to take antiderivatives of are straight up powers of x, right? Like x squared, x to the 5, x to the 1/2, 1 over x. But I don't know how to take antiderivatives of big quotients like this. I cannot just take the antiderivative of the bottom and the antiderivative of the top. That doesn't work. For the same reason that when you take a regular derivative, you don't just take the regular derivative of the top and the regular derivative of the bottom, right? You need a special rule. We can get around this issue here by splitting up the fraction. This is x cubed over x squared minus 2x squared over x squared plus 3x over x squared minus 5 over x squared. And then each of those pieces can be simplified. So still no antiderivative work yet, just algebra. X cubed over x squared that's x, minus 2 times x squared over x squared, oh, that's 1, plus 3 times x over x squared, that's 3 times 1 over x, minus 5 times 1 over x squared. Is everybody with me so far? Here, the rule that I'm using is just this simple rule for fractions, just the algebra of fractions, that a plus b over c is the same as a over c plus b over c, right? So this sum and difference upstairs can be broken up. You can split fractions up over their numerator. That's what this says. Okay. I'd like to tuck this in somewhere it's not in the way, maybe here. I'm almost to a place where I can write down my antiderivative now. The only piece that I need to rework still is this. So little f, written in its easiest form to antiderive, is x minus 2 plus 3 times 1 over x minus 5 times x to the negative 2. Now, each one of these individual pieces, I know how to find an antiderivative of. So capital F, my antiderivative, is this guy. This is x to the 1. So when I apply the power rule to him, I'll get x to the 2 over 2 minus 2. Well, who has derivative 2? That's just 2x, right? Plus 3 times 1 over x. So that's plus 3 times the natural log of the absolute value of x. Minus 5 times, same rule works great here. This is going to be x to the negative 2 plus 1 divided by negative 2 plus 1, like that. So what do we get? X squared over 2 minus 2x plus 3 ln absolute value x minus 5 times, this is negative 1, so x to the negative 1, and then I'm dividing by negative 1, which will change this minus to a plus. And really I should have my plus c plus c. So here is your most general antiderivative for this function. And we never would have had a chance of getting there unless our first step was to split the thing up like this. I want to emphasize that you cannot take the antiderivative of the top and bottom separately. That shit doesn't work, just like it doesn't work for regular derivatives. So while you guys are writing or thinking of questions, I'm going to turn on my fan because I'm starting to sweat. Cool side of the pillow. Okay. Thoughts, questions, comments, concerns? I want to know what's going on in your brain. If it's all good, you can tell me it's all good. I just want to know what's going on in our heads here. Is there anything that feels strange? Is there anything that feels silly? Like, why did we do this? I appreciate the thumbs up. That helps. Any other feedback at all?
Can't we just keep going backwards, just like how we do normal derivatives? Like, what if we just keep doing antiderivatives? Like, would we have to do that? And if we do, why?
Yeah, sure. No, that's a great question. One of my favorite examples is actually related straight to that. Okay, so you know in like movies and cartoons and stuff, when someone goes to like make a basketball shot or shoot a gun at a target or something far away, they'll show them doing a bunch of little calculations in their head and then boom, make the perfect shot. They're doing antiderivative calculations. That's the joke in those things. So yes, you can do this more than once. And one of the most common applications of doing this more than once is going from information about acceleration all the way back up to information about position. So here's one of my favorite examples. I'll start by saying, recall that if s of t is a particle's position, v of t is a particle's velocity, and a of t is a particle's acceleration, where the particle is moving in one-dimensional motion, right, either straight up and down or straight along a line, then s primed is equal to v, v primed is equal to a, and because s is v prime, or s primed is v, this is the same as s prime prime. In other words, position is the antiderivative of velocity, and velocity is the antiderivative of acceleration. So I could tell you that the acceleration, is there one L or two L's in acceleration? That's embarrassing that I can't remember how to spell it. I want to say there's two L's, but I feel like I also always misspell. Acceleration of a particle moving along a straight line, moving in one dimension, is a of t equals, let's say, -16, because this is, well, let's use the other units. Let's say it's -9.8. These are the SI units for gravitational acceleration here on the surface of the Earth. And the initial velocity v of 0, let's say this is 2 meters per second. The units here are meters per second squared. And the initial position is s of 0 is, let's make it 1,000 meters. So here's the situation. You're up in a plane 1,000 meters above the ground. You throw your brave ass out the plane, jumping up at a rate of 2 meters per second. Describe how far you are from the ground every second after that, and maybe even find the moment from you when you hit the ground, assuming you don't have a parachute. This is a morbid example, but this is how gravitational acceleration works. Acceleration due to gravity is a constant, 9.8 meters per second squared, here on the surface of the Earth. It depends on your altitude a little bit, but this is the standard. I would begin by taking the antiderivative of acceleration to go back to velocity. So v of t is the antiderivative of a of t, right? Because v primed is a, v is the antiderivative for a. So I need an antiderivative for the constant function -9.8. That would be -9.8 t. And I have to slap on a plus c here.
So if we were to go backward one more time, like what would happen to the constant? Because we basically have to do like, going back to the derivative of the constant. So would there be like another variable for another constant, or is it just carrying over? Like,
No, there would be another variable for another constant. But here, I've given you the information you need to solve for each of those constants as you go. So you're right. If I wanted to just take another antiderivative to get to s, the c would become c times t, and then I would need another constant, plus d or something like that. But here, because we have this bit of information, I can solve for c. These are called initial value problems. So v of 0, I know is, on the one hand, negative 9.8 times 0 plus a constant, right, plus c. But on the other hand, I know it's 2. So 2 is equal to negative 9.8 times 0 plus c. In other words, c is equal to 2. So if I gave you just this information, just the information that I'm highlighting in the blue box now, the best answer you could give me for the velocity function is v of t equals negative 9.8 t plus 2. When we took our antiderivative, there was this constant c, and then this bit of information they gave us, the initial velocity, the value of the velocity function when you plug in t equals 0, they told me is 2. So I plugged in 0 for t, and I set that equal to 2. 9.8 times 0 is 0, so this is just 2 equals c, so c is 2. Then I take that value of c and I plug it back in here. Now here is my complete velocity function. You want to know how fast you're going or in what direction any moment from the second you jump out the plane at time t equals 0, you plug the time into this function and it will tell you. At time t equals 0, my velocity would be 2 because this piece would be 0. At time t equals 1, just 1 second later, my velocity would be like negative 7 because it would be negative 9 plus 2. It's like negative 7. So this is your velocity function. And then if you want to, like you're asking, do it again, take another antiderivative. S of t, we know, is the antiderivative or an antiderivative of the velocity function, right? Because s primed is v, s is an antiderivative for v. So I'll go ahead and take my antiderivative of v. V is this. The negative 9.8 comes along for the ride. Antiderivative of t is t squared over 2 plus an antiderivative for 2 is 2t. And now here you would add on another constant, plus d. And in order to sort out that last constant, I use this last bit of initial value. S of 0 is 1,000. So S of 0, well, on the one hand, it's definitely what you get when you plug in 0 for t here. That's negative 9.8 times 0 squared over 2 plus 2 times 0 plus d. This stuff is all 0, right? 9.8 times 0 is 0. 2 times 0 is 0. And then S of 0, I've been told, is 1,000. So this is the same as saying 1,000 equals 0 plus d, or just d. So your final answer here, S of t is, you take this function and you plug in the value of d we just found. Negative 9.8 times t squared over 2 plus 2t plus 1,000. That is your position, your height, t seconds after jumping out of the plane. And all projectile motion problems go the same way. all of those, you throw a book off the tower or whatever problems that you remember from pre-calculus, they're all cooked up using this method. There are a lot of other good answers to your question. What happens if I do this again and again and again? If you think about polynomial functions, every polynomial you can differentiate again and again and again until it becomes 0, right? You differentiate a quadratic function twice and you'll get a constant function. You differentiate that one more time, you'll get 0. So in some sense, differentiating a function makes it less smooth and curvy, and integrating a function makes it more smooth and curvy. I say integrate. Integrate is the word for antiderive. I'm sorry, I shouldn't be using that word yet because we haven't talked about it. Differentiating a function makes it less smooth and curvy. Anti-differentiating a function makes it more smooth and curvy. I've got a special example to show you to try and convey that concept too. But first, I'd like to take any questions we have on this, because this sort of physics thing is a pretty big deal. It's also our first time solving what's called an initial value problem, where I give you some information about the derivative, or in this case, the second derivative, and then also the information you need to solve for the constants that show up as you anti-differentiate.
You said before that like the CT, like if we were not given the initial or like V0, it would be CT. So on that part, how would we solve for CT if we were only given like the initial thing for D? I'm not sure if my question is very clear, but
No,
I
yeah,
don't
that's
know.
perfectly clear. So it's a really good question. And a great answer to that would come in the language of differential equations, but I'll say this. A of t here, this is the second derivative of the function you want, right? So we need to anti-differentiate twice to get back to s of t. Each time you anti-derive, you'll get a new constant. You need the same number of initial conditions as the number of times you need to anti-differentiate in order to solve for all the constants. So if I gave you just this, just the second derivative, and just this, just the information to solve for one of the constants, you wouldn't actually be able to do the job. There is not a unique solution to that problem. There are many solutions to that problem, and characterizing them can be quite tricky. So I'll show you how to do a general antiderivative through 2 steps without solving for the constants. But the answer is, if you want to solve for all the constants, you need the same number of points, initial conditions along the way, as you have derivatives that you're going to undo. So if you want to undo 2 derivatives, you need 2 initial conditions. If you want to undo 3 derivatives, you need 3 initial conditions. Otherwise, you will end up with just extra constants floating around for which you cannot solve.
Okay, that makes sense. Thank you.
Cool. Yeah, this is neat. This is actually where the study of dimensionality in differential equations comes in a certain way. There's a lot of beautiful linear algebra here having to do with the dimension of the solution space and the number of initial conditions provided. You will see more of this in MAP2311 if you choose to take it, which I highly recommend. It's a great class. All right. So one more example here where we're doing multiple antiderivatives. This time, we're just going to leave the constants. All right, so what if there are no initial conditions given? What's the best we can do? So f of x, let's say, is 1 minus 2x. And let's find, sorry, f double primed is 1 minus 2x. Find a formula for the original function f of x using c for the first constant and capital D for the second constant. Problems like this definitely do show up, although not usually in application or real-world problems. In real-world problems, you'll have the information you need to solve for C and D. But sometimes we just like to do this as an exercise. So if I jump in and anti-differentiate once, that will take me from f double primed to f primed. An antiderivative for 1 is 1x minus an antiderivative for 2x is 2x squared over 2, just using my power rule here, and then plus c for my additive constant here. The 2's cancel. So I would say f primed is x minus x squared plus c. So anti-differentiating once took me from f double primed one step back down the ladder to f primed. And then if I want to go one step back down the ladder further, that will take me to regular f. So I anti-differentiate again. X will become x squared over 2. Minus is minus. X squared will become x cubed over 3. Plus c will become plus cx. And then because I'm taking another antiderivative here, we get a plus another constant. We'll call it plus d, because that's what they asked us to do. Cool stuff, right? And without information, I cannot solve for C and D. In order to solve for C and D, I would need 2 pieces of information. 1 piece of information for each constant. If you told me f primed of 0 is 5, or f primed of 1 is 2, or whatever, you gave me a particular value of f primed, then I could use that to solve for C. And if you told me f of 0 is 7, or f of 1 is -3, I could then use that information to solve for D after first solving for C and plugging it in. Okay. I want to show you how to anti-differentiate one more class of functions while we're here today. We now know how to, we can anti-derive or anti-differentiate any sum or difference of power functions. Right, anything that's polynomial or polynomial-like, anything that we can write as like a constant times x to some power plus another constant times x to another power and so on. What other giant family of functions do we care about a lot in calculus? Trig and exponential. Right, most of our functions are either power functions or sum thereof, or trig functions, power functions, exponentials glommed together in some way. So once we have all of these, we'll have a pretty big family of stuff we can handle. Exponentials first, because they're easier. If f of x, little f, is e to the x, then who differentiates to e to the x? What would be a good antiderivative for e to the x? I know you guys can do this.
E to the x.
Yeah, if we take the derivative of e to the x, we get e to the x back. So e to the x is not only its own derivative, it's its own antiderivative. Okay, that's good. We should hold on to this for sure. What about other base exponentials? Like 2 to the x, 5 to the x, b to the x in general. It's a little harder. Let me remind you, because we may have forgotten, that the regular derivative of b to the x is b to the x times the natural log of b. So everybody remember this? It's okay if you don't at the moment. The justification for this came from the chain rule. We're able to treat b to the x as e to the x times the natural log of b, and then differentiate using the chain rule. If you forget this, you can be forgiven, but please remember it. All right, please choose to remember it now, because this is what will inform us about the antiderivative. Just like when I want to anti-differentiate something like x squared, I think about the forward derivative. Okay, it's 2x, so antiderivative of x would be x squared over 2. If I want to anti-differentiate b to the x, I think about its forward derivative. When I regular differentiate b to the x, I get b to the x times the natural log of b. Natural log of b is a constant. So an antiderivative for b to the x, and you must remember this, is b to the x times the natural log of the base. It's true that most of the time when we work with exponentials, they will be base e. They will be natural exponentials, but not always. This is coming from, or this is, you can think of this as because the forward derivative of b to the x is b to the x times the natural log of b. Oh shit, I fucked up. God damn it. Divide by this. Divide by this. Sorry. The forward derivative of b to the x is b to the x times the natural log of b. So the antiderivative of b to the x is b to the x divided by the natural log of b. I'm so sorry. Talking and writing. So for example, if little f of x is 2e to the x plus e times 2 to the x, then the most general antiderivative is capital F. Antiderivative for 2e to the x, the 2 comes along for the ride, and the antiderivative of e to the x is e to the x, plus, now here I'm just being cheeky, e is the multiple, and the antiderivative for 2 to the x is 2 to the x over the natural log of 2. Okay. So the base e exponential is easy. He doesn't change no matter what direction you're going on the derivative ladder. Other base exponentials, when you want to antiderive them, the antiderivative of just 2 to the x on its own is 2 to the x divided by the natural log of 2. this is the more general rule. You may notice the word general in mathematics means something different than it does in common parlance. General means works everywhere, right? The most general rule is this one. If you plug in e for b, then you get e to the x over the natural log of e. Well, the natural log of e is 1. So if you remember this formula, you don't need to remember this one separate. But most people do, because you use this one way more than you use this one. But both are important. Questions on antiderivatives of exponential functions? It's not too bad. Let's try one more. We got space for one more. Let's do another one real simple. Find an antiderivative. Oh, I should have a plus c here, sorry. Yeah, this last guy, because we want the most general antiderivative. I needed my plus c. If I want to antidifferentiate 1/3 to the x, which is the same as 3 to the negative x, that would be capital F equals 1/3 to the x divided by the natural log of 1/3. And then we should slap on our plus c here. Okay, moving along. Trig functions. I'll leave this page just for a second in case anybody is still writing. But we are going to move to trig functions. You know the derivatives of sine and cosine. So antiderivatives for sine and cosine, those aren't too bad. They just kind of go back and forth. You just got to be really careful about that negative. All right, changing pages. Trig functions. You know the derivative of sine is cosine, and the derivative of cosine is sine. So if little f of x is cosine, then big F of x, an antiderivative for cosine, who differentiates to cosine? Oh, well, that's sine. And the most general would be sine of x plus a constant. Because when you differentiate this, you get this. If little f is sine of x, who has derivative sine? We want to say cosine, right? But the derivative of cosine isn't sine, it's negative sine. So to cancel that negative, we need another negative. Antiderivative for sine is negative cos x plus c. So it's really exactly backwards from the regular derivatives. Regular derivatives differentiate cosine, you get negative sine, so you got to remember to slap on a negative there. For antiderivatives, antiderivative cosine is just regular sine, no negatives needed. Antiderivative of sine is negative cosine. Antiderivative of secant, much more challenging. Antiderivative of tangent, believe it or not, is a little bit challenging. I'm going to show you a few other antiderivatives that are kind of easy at the same level these are, and then I will get to the other ones. Can you think of anybody whose derivative is secant squared?
Tangent.
Good. So an antiderivative for secant squared is tangent, or tan x plus c. And an antiderivative for secant tangent is going to be secant, because the derivative of secant is secant tangent. These are kind of the easy ones. Cosecant and cotangent follow similar patterns. I'll let you discover those yourself. They're not hard to figure out. The other guys, so these are the kind of easy ones. Less easy. Rather than just giving you the result here, I'm going to ask the question. What is the derivative of negative natural log of cosine? Remember back when we did some of those weird log derivatives, we're like, oh shit, this looks like this. Surprising, right? Like the logs all went away and we just got a regular trig function. Well, now it's coming back at us. The negative is going to come along for the ride. The derivative of the natural log of cosine is 1 over the inside times the derivative of the inside. The derivative of cosine is negative sine. So the two negatives will cancel, and you just get sine over cosine, which is tangent. In other words, an antiderivative for tangent is negative natural log of cosine. And really, we should use absolute values because cosine is not always positive. I will show you a way of getting this after we learn about section 5.5. It's quite a ways away. The derivative, the antiderivative, sorry, of secant is similarly challenging, and it's going to have to wait also. So don't stress about this for now. It's good to know, and we've seen this result before, that if you differentiate the natural log of sine or cosine, you get something like tangent or cotangent. So it's nice to see now. I'll let you think about what might differentiate to secant or cotangent or cosecant. The secants here are actually quite hard. Secant and cosecant. The cotangent one, I think you could probably figure out based on what we just said here. But the others are quite difficult. So I think this is a good place to leave it for today. There's not a whole lot else that you need to handle the antiderivative stuff for your homework. In fact, there isn't anything else you need to handle the antiderivative stuff for your homework. A word of warning, though. Oh, no, don't worry, Elisa. Yeah, it's taking me a little bit of time to get those done. I'm sorry. So a word of warning, antiderivatives in general are much harder than forward derivatives. And there are a few others that I should show you before we go inverse trig. So all of these you can cook up using what you know about forward derivatives, but I'd like to just share them with you. If f of x is 1 over the square root of 1 minus x squared, you will never get an antiderivative for this following power rule stuff. It's way too complicated because the square root has subtraction underneath it. It doesn't work nice. But you know who differentiates to that just by thinking about your inverse trig functions. That's the derivative of the inverse sine function. Negative 1 over the square root of 1 minus x squared. That's the derivative of the inverse cosine function. And 1 over 1 plus x squared, that's the derivative of the inverse tangent function. So just like you had to pretty much straight up memorize or remember through whatever mechanisms you like the derivatives of trig functions in the regular direction, you need to just remember these as well. You'll remember them from practice, right? These are the kind of fundamental antiderivatives for trig and inverse trig functions that you just got to know. And with enough practice, you will get there. All right, this is where I'm going to leave you guys for today. Do not worry about the area problems in your homework. The homework has been extended to next Wednesday. Next Monday, I will teach you how to solve those area problems. Next Wednesday, we don't actually have class. And then next Friday, I'm going to introduce some notation for antiderivatives that works a little better than this arrow. All right.
Why don't we have class on Wednesday?
Next Wednesday is Veterans Day. So there isn't an official class on that day. The college is closed. I'm not allowed to have a class on a day when the college is closed. All right, I know you guys are anxiously awaiting grades. If you have study guide grades that you haven't gotten back yet, I'm sorry, I'm swamped with those things from like 4 different classes. I'm going to grade the exams first. So if you didn't get a grade on your study guide back before the test, I'm going to go ahead and grade the exams because I know that's what everybody's most worried about. Then I will go through and clean up the study guide grades. But as long as you did all the problems, your study guide grade is going to be a full score, so don't stress. The exam grades, I will get back to you as always within 1 week of the exam date. If you have any questions, you want to talk to me about anything, you can come see me in office hours. Today's a Friday, so those are 2 to 3 p.m. Any last minute questions before we end class? All right, work hard on your antiderivatives. The first third of Calc 2 is all antiderivatives, just done with a slightly higher brow thing. So this shit is fundamental to your next class. We're not just pissing in the wind here. This is stuff you're really gonna need, not just in this class and on the final, but in the class after it. So put some love in here. It will serve you well in the future. If you're stuck on anything or having a hard time with anything, even if it's from an old assignment, please do not hesitate to reach out for help. I am here to help you. And that is it. I will see you guys on Monday. All right, take care. Be nice to each other about the election. I know this shit is stressful for everybody, regardless of your political perspectives. So try to remember to be kind. All right, take care, guys.